let's take a look at this new equation we have for describing our general second order systems. So let's note that we can find our pole locations, by using the quadratic equation on the denominator of our transfer function g of s. So doing that, we get s1 and 2 equal negative zeta omega n plus or minus omega n times the square root of zeta squared minus 1. So those are the two roots of our denominator, which are the poles of our g of s. So what we can do now is we can consider different values of our zeta, our damping ratio, and see how the poles, and therefore our response type, are changing. So first, let's consider what happens if we have a zeta value equal to 0. So if we have zeta equals to 0, what are our two poles going to look like? Well, S1 and S2, if we have this is 0, this term is going to go away. If we have 0 here, then we just have negative 1, so that becomes plus or minus j omega n, where of course j is equal to square root of negative 1, which is our imaginary number. So if we have two imaginary poles, we know that that means we have an undamped response. So two imaginary poles, which tells us undamped response. All right, so pretty easy. So let's look at another range. So let's say for zeta between 0 and 1. And so why am I choosing 1? Well, first of all, I obviously know the material and where it's going, but even if I didn't, I could look at our argument of the determinant here and know what range of zeta is going to give us different types of poles. So in this case, we're going to have a non-zero part for that first term, so we're going to have that negative zeta omega n plus or minus. Now, zeta squared minus 1 is going to be a negative number. So what we can do is we can multiply by negative 1, factor out a j, and then we have omega times square root of 1 minus zeta squared. So I've just flipped the order in that determinant. So here what we see is we have two complex poles. And so as we saw previously, complex poles correspond to an underdamped response. Okay, so we know if zeta is in that range, we have an underdamped response. So let's keep on increasing our zeta. So let's say if we have our damping ratio zeta equal to 1, what does that give us? Well, looking at this equation for our poles, we plug in a 1, so we have negative omega n, so S1, 2, for this first term we have negative omega n, and now plugging in our zeta here, we have 1 minus 1, which is 0. So we just get negative, and I forgot my subscript n, so we get negative omega n plus or minus 0. So of course that's going to be the same, so we just get both of them are equal to the same thing of negative omega n. So in this case we have real repeated roots, or real repeated poles of our g of s. And so what this means is we have a critically damped response. So then finally, we can let our zeta be greater than 1 and see what that does to our two poles, S1 and S2. So again, we're going to have a non-zero term out front, so we have that negative zeta times omega n plus or minus. And now, looking in this determinant, because our zeta squared is greater than 1, that's a positive value. So we just basically keep what we have written there, omega n times square root of zeta squared minus 1. And these are going to be two real poles. And so as we saw before, two real poles correspond to an overdamped system. And so we can see that that's pretty cool, because now just by knowing the value of our damping ratio zeta, we know what type of response to expect: undamped, underdamped, critically damped, or overdamped. And so that's certainly easier than having to explicitly find our poles and then from there determine what type of response we're going to have.